Okay guys, so today the Cauchy-Schwarz inequality in its regular and Engel form. Proofs, problems, everything you might want. Let's roll. Okay guys, so the Cauchy-Schwarz inequality states that whenever we have two sequences of positive real numbers, namely ai's and bi's in my example, then the sum of all of the terms of the ai sequence squared multiplied by the sum of all of the terms of the bi's squared is going to be greater than or equal to the square of the sum of the products of all of the symmetrical terms of those two sums multiplied together. So in other words, a1 squared plus a2 squared all the way up to an squared multiplied by b1 squared plus b2 squared all the way up to bn squared is going to be greater than or equal to a1 times b1 plus a2 times b2 all the way up to an times bn, everything squared. And that's exactly what we would like to prove right now. Okay guys, so let's get right to it. Well, so for the proof of the Cauchy-Schwarz inequality in its regular form, well, I would like to show you guys a pretty neat trick that is used to prove this inequality that I just absolutely love, and it's just, you know, the essence of like Olympiad level maths. So let's consider a quadratic equation. Let's consider a quadratic equation because of the form sum a multiplied by x minus b everything squared. Well, we know that this quadratic is always greater than or equal to 0 because, well, whatever is here inside this parenthesis, no matter if it's negative or it's 0, well, this entire thing after being squared is always greater than or equal to 0. Well, if a quadratic is greater than or equal to 0, it means that its discriminant, the delta, is going to be less than or equal to 0. Okay, well, that's pretty interesting. I mean, can we even use this kind of fact here to use this Cauchy-Schwarz inequality? Yes, we can. Let's just go on and replace this a right here with some ai from our sequence ai, so positive real numbers, and this b with bi's, yeah, also from one of our sequences of positive real numbers. And now let's just kind of go on and take a sum over all of those terms of those sequences. So what we'll end up with is a sum from, let's say, once again, I being equal to 1 up to n of ai's multiplied by x and then minus bi's and then everything squared. Well, what is this thing? We can just go on and kind of multiply out this entire parenthesis here inside of this sum, getting this sum from I equal to 1 up to n of ai. Oh, sorry, this I is not quite beautiful. So ai squared times x squared minus double ai times bi times x and then plus bi squared. Okay, but the nice thing is that we can just kind of go on, split this entire sum into three separate sums because we are just kind of adding and subtracting terms here inside of it. So let's just go on and do it. We can partition this sum into three separate sums, namely the sum from I being equal to 1 up to n of ai squared times x squared, then negative sum from I being equal to 1 up to n of double ai bi x and then plus another sum, this time once again from I being equal to 1 up to n, but this time from bi's squared. And well, the nice thing is that what we can do here is just kind of go on and factor out those x's. I mean, we can just go on and factor them out of those sums altogether. So let's go on and do it. Maybe we'll get something interesting. Yes, we will. I mean, spoiler alert, we will. So that's gonna be equal to x squared multiplied by the entire sum from I equal to 1 up to n of ai's that are gonna be squared as they're going to be squared, then negative x multiplied by, let's say, just 2, I'm going to take out the 2 as well, sums from I being equal to 1 up to n of ai multiplied by bi, and then, well, there is no x to be taken out from here, so just I'm going to be adding this sum from I being equal to 1 up to n of the squared bi's. Well, the nice thing is that this thing right here is also a quadratic equation. Is also a quadratic. I mean, this sum from I1 up to n of ai squared is just gonna be the leading coefficient. This 2 sums from I equal to 1 up to n of ai bi is just gonna be the coefficient that is next to the x in the first power. So the b in the regular quadratic equation form, I think, and this is gonna be our constant term, our c, this sum from 1 up to n of bi's squared. Now, the nice thing is that this entire sum is, well, also gonna be greater than or equal to 0 for all of the x's, because it's just equal to ax minus b, everything squared, and that's, as I've said earlier, greater than or equal to 0. So that means that the discriminant of this entire quadratic equation, is gonna be less than or equal to 0. So, well, let's go on and try and calculate this this discriminant. You might already know what I'm going at. So, what's the coefficient? What's the discriminant? What's the discriminant of a quadratic equation? Well, that's just b squared minus 4 times the leading coefficient times the constant term. So in our case, that's going to be equal to, that's our a, that's our b, yeah? That's going to be the sum from I being equal to 1 up to n of ai bi, and then everything squared, and I should have also put 2 right there, yeah? Then it's gonna be negative 4 multiplied by the sum from k being, I being equal to 1 up to n of, that's a, so ai's squared, and then the constant term, which is the sum as I goes from 1 up to n of bi's that are squared. And this entire thing is going to be less than or equal to 0. And, well, there's nothing stopping us from just taking this entire product of those parenthesized sums to the right-hand side of this inequality and getting that 4 times the sum from I being equal to 1 up to n of ai bi is going to be less than or equal to, well, this entire product. I'm just gonna be copying because I'm too lazy to write that down again. So what we can do now is just nicely cancel out those 4's by dividing both sides of this inequality by a factor of 4. And, well, this is the Cauchy-Schwarz inequality. I mean, just look at it. This sum from I being equal to 1 up to n of ai bi is just gonna be equal to a1 times b1 plus a2 times b2 all the way up to a and bn, and then everything is going to be squared because of this square I didn't put here. Yeah, so now is better. Now it's much better. Yeah, and there's going to be less than or equal to, well, this guy right over here is just going to be the sum of all of the a's that are going to be squared. And then we will just multiply this sum by the sum of all of the b's that are also gonna be squared. And, well, this guy right here is exactly the same thing we had right over here. So the Cauchy-Schwarz inequality. So once again, what did we do to prove the Cauchy-Schwarz inequality? We just kind of consider the quadratic, which is ax minus b squared, which is always greater than or equal to 0, and that has always a discriminant which is less than 0. Replace the a and b here with ai's and bi's from our original. I'm pointing too much arrows at those poor sequences right over there. putting them in the spotlight, our sequences of positive real numbers. What we did then is just kind of played around with this sum of all of those quadratics to arrive at a nice conclusion that the sum of all those quadratics is just going to be a quadratic itself, a quadratic that is going to be greater than or equal to 0, so it will have a discriminant that is less than or equal to 0. We calculated that discriminant right over here in terms of sums involved in the Cauchy-Schwarz inequality, getting pretty novelly that, well, the Cauchy-Schwarz inequality holds absolutely pretty absolutely nicely. So we can just go on and put a nice checked box right here. Okay guys, but the Cauchy-Schwarz inequality does not have only one form, because there's the so-called Engel form of the Cauchy-Schwarz inequality, which looks something like this. I mean, it's also in America, I think, called Titu's lemma, but well, Americans just have to do everything differently. That's always, well, whatever. So it states that whenever I have two sequences of positive real numbers, let's say a's and b's, then the sum of fractions of the form ai squared over bi, which is basically something like a1 squared over b1 plus a2 squared over b2 plus an squared over bn, can be greater than or equal to the squared sum of all of those a's divided by the sum of all of those b's. And I would actually like to prove this thing right now as well. Okay guys, so the proof of the Engel form, the Cauchy-Schwarz inequality, is not very long because it's just an immediate consequence of the regular form of the Cauchy-Schwarz inequality. As you can see, we've got this entire inequality. Maybe I will just kind of rewrite it. So a1 over b1 all the way up to an squared over bn is going to be greater than or equal to the squared sum of all of those a's divided by the sum of all of those b's. You can just kind of see that what we can do here is just multiply both sides of this inequality by the sum of all of those bi's, and so by doing that what we'll get is just the sum of those a1 squared over b1 plus all the way up to an squared over bn, and everything will be multiplied by the sum of all of those b's up to bn. It's going to be supposedly greater than or equal to the sum, the squared sum of all of those an's. However, as you can see, this is exactly what the Cauchy-Schwarz inequality states, because what we see right over here, this a1 squared, is just the square root of a1 squared over b1 multiplied by b1. This an right over here is just a square root of an squared over bn multiplied by bn. So well, we can see that this is exactly the Cauchy-Schwarz inequality, but we've just kind of divided by the second sum, the sum of all the b's. Okay guys, so for the first problem, we would like to take ourselves a, b, and c that are positive real numbers, and supposed to prove that 3 times a squared plus b squared plus c squared is greater than or equal to a plus b plus c all squared. Okay, so how are we supposed to do it? Well, the nice thing would be to interpret this 3 right over there as 1 plus 1 plus 1. Well, why is it so? Because this is a parenthesized sum of 3 things, just as well as this a squared plus b squared plus c squared. So maybe some Cauchy-Schwarz would, you know, go in handy right here. So let's try and do this. I would like to rewrite this 3 as, once again, 1 plus 1 plus 1. And then I would like to also write this a squared plus b squared plus c squared right over here. Well, by the Cauchy-Schwarz inequality is going to be greater than or equal to a multiplied by 1 plus b multiplied by 1 plus c multiplied by 1, everything squared, but this thing is just equal to a plus b plus c, everything squared, just exactly the same thing as we had right over here, and so our inequality is nicely proven. Okay guys, so for the second problem, would like to finally prove the QMAM inequality, which states that whenever we have a sequence of positive real numbers, let's call that sequence xi's, we have that the square root of the sum of squares of the terms of that sequence divided by the amount of those numbers, so by n, is greater than or equal to the arithmetic mean, so the sum of those of that sequence of terms divided by the sample size. Okay, so how are we supposed to solve it? I would like to use a quite of a similar trick to the one we used in the previous problem. So first of all, let's just go on and square both sides up so we get rid of this awfully looking square root right here. So doing that, what we'll get is here we will just have x1 squared and the sum all the way up to xn squared, everything divided by n. And the right hand side of this inequality, what we're gonna get is just the arithmetic mean. That's pretty nicely squared. But now, oh sorry, I should have put n here. But now what we can do is just kind of distribute this second power both to this n and this sum right over here. So kind of rewrite this entire statement as the sum of those x's to the second power divided by n to the second power. And what we can do now with that is just multiply both sides of this inequality by n squared. And so after doing that, we will get on the left hand side of this inequality the sum of all squares of those positive real numbers multiplied by n that is greater than or equal to the squared sum of all of our xi's. But now I would like to use the same trick we used before and just rewrite this n right over here as just 1 plus 1 all the way up to the nth one, so we have a 1 appearing n times in this sum. And so after doing that, our inequality is gonna look like this: x1 squared up to xn squared is gonna be multiplied by 1 plus all the way up to the last one, and we've got this 1 appearing n times here, and this entire product is gonna be greater than or equal to x1 up to xn. This should not look like a wavy line, all squared. However, this thing right here is, well, just the Cauchy-Schwarz inequality, because this x1 right over here is just equal to the square root of x1 squared multiplied by 1, which is x1 multiplied by 1, just as this xn right here is just the square root of xn squared multiplied by 1, which is just xn multiplied by 1. So we see that the Cauchy-Schwarz inequality directly implies that the QMAM inequality holds as well, and that would be all for the second problem. Okay guys, so for the third problem, we would like to take in x, y, and z that are positive real numbers. We're supposed to prove that the square root of 3x squared plus xy plus the square root of 3y squared plus yz plus the square root of 3z squared plus zx is less than or equal to double x, y, z. Perfectly. So how are we supposed to solve this one? First of all, I would like to rewrite the left-hand side of this entire inequality in terms of cyclic sum notation. If you don't know what a cyclic sum notation is, then check out a video, I think is the previous one, in the MOC playlist. Awesome. So this thing right here, so the sum of those square roots is just gonna be the cyclic sum of the square root of, now let's just take out this x, and let's factor out this x, is going to be x multiplied by 3x plus y. Lovely. But by the Cauchy-Schwarz inequality, we know that if we were to now square this entire sum out, then this would be less than or equal to the cyclic sum of x multiplied by the cyclic sum of 3x plus y. So let's just use this fact, but let's not square this guy out. Let's just take those guys on the right hand side of the inequality under a square root. Okay, so that's a lovely thing to, like a lovely conclusion to arrive at, yeah, okay, because now what is the cyclic sum of x when we're just cycling through x, y, and z? Well, that's just x plus y plus z. What about the 3x plus y, the cyclic sum of 3x plus y through x, y, and z? Well, that's just 3x plus y plus 3y plus z plus 3z plus x, which is 4 multiplied by x plus y plus z. And so this entire thing right here, this entire square root of this product of those awful parenthesized sums is just gonna be the a square root of x plus y plus z multiplied by 4 multiplied by x plus y plus z, which is just the square root, which is just the square root of 4 times x plus y plus z all squared, which is equal to double x plus y plus z, which is pretty nicely equal to the exact upper bound we were supposed to prove for the awfully looking sum of square roots. That's the end. Okay guys, so for the fourth problem, the 1995 IMO inequality question, which is as follows. We're supposed to, given that a, b, and c are positive real numbers such that the product is equal to 1, prove that 1 over a cubed times b plus c plus 1 over b cubed multiplied by a plus c plus 1 over c cubed multiplied by a plus b is greater than or equal to 3 halves. Okay, so how are we supposed to do it? Well, I think that those fractions should ring a bell that maybe it will be possible to, in the future, use the Engel form of the Cauchy-Schwarz inequality, or at least to try and get this entire sum of those fractions to a form where using the inequality would make any sense, because, well, honestly, right now, it doesn't do make any sense at all, because what we would get after applying the Cauchy-Schwarz in Engel form directly here would be just 9 over the sum of all of those awful denominators, which, even given the condition that the product is equal, that the product of a, b, and c is equal to 1, would not give us anything at all. But if we manage to maybe get a little bit of those denominators and get it to the numerators, so that maybe after applying the Engel form, the Cauchy-Schwarz inequality stuff in the numerator will cancel at least a little bit of the stuff in the denominator, then maybe it would make sense to use that inequality. So, well, do you think we would be able to do any kind of a manipulation that would make us end up in a place like this? Well, I think there would be one. For example, let's say that we would take ourselves 3 variables, x, which is equal to 1 over a, y, which is equal to 1 over b, and z, which is equal to 1 over c. There's no problem in doing that, as a, b, and c are just positive real numbers. X, y, and z are also positive real numbers, so we're not leaving the set we're trying to prove this statement on. Well, this condition a, b, times c is equal to 1 implies that x times y times z also will be equal to 1, and so let's just go on and plug this into our beautiful inequality. So first of all, I would like to rewrite this entire sum of fractions in terms of the cyclic sum notation. Again, if you're not familiar with it, then just check out a video of mine on notation. So that's gonna be the cyclic sum of 1 over, and now 1 over x cubed multiplied by 1 over y plus 1 over z. So now what we can do is just kind of multiply everything right here by, we could multiply the numerator and the denominator by an x to the power of 3, which would not change the value of this thing a bit. So let's go on and do this. So by doing that, what we will arrive at is x cubed in the numerator and just an x cubed and just, well, 1 over y plus 1 over z in the denominator. That's all in a cyclic sum, which I probably should have said earlier. Okay, but it's all in a cyclic sum right over here. And now we could just get those y's and z's in the denominator to a common denominator, which will give us a cyclic sum of x cubed divided by z multiplied by, z plus y divided by z times y, but this thing is just equal to the cyclic sum of x squared divided by z plus y. Okay, that's pretty lovely, because now we can use this thing, and probably now, well, using the Engel form, the Cauchy-Schwarz inequality will be a little bit easier, I think, because, well, we have a square here in the numerator, and we have a sum of z plus y in the denominator. So now, when we apply the Engel form of the Cauchy-Schwarz inequality to this sum, we'll get as greater than or equal to x plus y plus z, everything, sorry, not everything cubed, but everything squared, and everything also divided by the sum of double x plus double y plus double z. And so we can just go on and cancel out this square and this sum nicely, being left with x plus y plus z, x plus y plus z, everything divided by 2. But this thing right there is by GM inequality greater than or equal to triple the cube root of x, y, z all over 2, but what's x times y times z? Well, that's just a 1, so it's all equal, so it's all greater than or equal to 3 over 2, which is exactly the lower bound we were supposed to prove on this beautiful sum of fractions. Lovely. Let's go further. Okay guys, so for the last problem we are given 4 positive real numbers a, b, c and d, and we're supposed to minimize the sum of their reciprocals given that the sum is equal to a1. Perfect. So first of all, what does it mean to minimize something? To minimize an expression means to find a lower bound for it, so a number such that the expression we're trying to minimize will never ever be less than that number. It means to find a lower bound for that expression. So you would like to find a number, let's say number k, such that the sum of the reciprocals of a, b and c and d is going to be always greater than or equal to k. Perfect. So now what I would like to do is, you probably guessed it already, I would like to use the Engel form of the Cauchy-Schwarz inequality, or the Titu's lemma as Americans like to call it, to derive the conclusion that the sum of the reciprocals of a, b and c and d is going to be greater than or equal to 1 plus 1 plus 1 plus 1 all squared and all divided by the sum of those denominators, which is a plus b plus c plus d, because those ones on the left hand side of this inequality are just equal to 1 squared. Well, there's no one to doubt it, I hope. Yeah. And so this entire thing is going to be equal, well, this sum of those ones is going to be 4, so this entire thing is going to be just a 4 squared, and so we say it's going to be equal to 4 squared over the sum of a, b, c and d, which is equal to 1, so 4 squared over 1, which is 16, and so we see that the minimum value for 1 over a plus 1 over b plus 1 over c plus 1 over d is 16. That minimum value is 16. That's exactly what we were supposed to find in this problem. Okay guys, so I really hope you enjoyed this video. Well, if you did, then don't forget to leave a like and subscribe to my channel, and see you next one. Bye.